So far, we have looked at three new first-order derivatives for functions of more than one variable: the gradient, the divergence, and the curl. So in this module, let's extend this idea and try to see what kind of second derivatives we can derive from the first derivatives which we have already worked out. And again, the key role uh, in sort of this derivation in us coming up with the second order derivatives is played by the del operator and its properties. So as a quick reminder, let me just write down the three first order derivatives we've already worked out. So we have del f, which is the gradient. We have the curl of a vector field, del cross v. And then we have the divergence of a vector field, del dot v. Now, these two, as we have been emphasizing, are themselves vectors, whereas the divergence is a scalar. So this is a scalar. Now let's ask ourselves the question, what kind of a derivative can we take of a scalar? So let's say we start with the divergence, which itself is a scalar. Now, what kind of a second derivative can we construct out of a scalar? It turns out that the answer is we can again use the del operator on a scalar and derive a new second order derivative, which is the gradient of del dot v, the gradient of the divergence. And that's pretty much the only thing we can do with the divergence, because the divergence itself, once we calculate the divergence of a vector, we end up obtaining a scalar function. This particular second order derivative, it's a second order derivative because you see del appearing twice. It turns out that this second order derivative we rarely find it being used in physical applications. So there's no special name associated with it, and we just write down that this is it sort of rarely finds applications. Rarely finds applications. Now let's look at the two remaining first order derivatives we have at our disposal. So one of them is the gradient. Now this gradient is a vector. So what kind of derivatives can we take of a vector? So this is a vector field, right? So we can take two kinds of derivatives of the gradient. One is we can take its divergence, right? We can take the divergence of a vector. And the other is we can take the curl of a vector. So let's take the divergence of this vector. The divergence of this would be del dot of the vector. The vector itself is del of f. And that's one we can construct. And we can take the curl. So we can take del cross del of f. Let me label each of these equations which we're deriving. So this is the first one we've obtained. This is the second order derivative we've obtained. This is the third one. And in the same way, when we have the curl, which is a vector, we can obtain two second order derivatives from this. We can take the divergence of the curl and we can take the curl of the curl. So the divergence of the curl will look like del dot the divergence, del cross v, and the curl will look like del cross v. So this is the fourth equation we have, and this is the fifth equation we have. And that pretty much exhausts all the possibilities which we have at our disposal. So given these first order derivatives, we can construct 5 second order derivatives. Now it turns out if we try to simplify each of these, that not all of them are, let's say, non-zero. And we'll now sort of explore a little bit more the divergence of the gradient, the curl of the gradient, the divergence of the curl, and the curl of the curl. We've already sort of mentioned that the gradient of a divergence is something which does give us a unique second order derivative, but somehow it really finds any application. So we're not going to focus too much on this particular derivative for now. Let's look at number 2 here, which is the divergence of the gradient. So we have del dot del f. And let's use what we know about the del operator to simplify and write this in the form of second order, something which actually looks like a second order derivative. So how do we do this calculation? And if you've looked at the previous module where we sort of calculated 3 different kinds of divergence of the position vectors of different variants of the position vector. So by now you must be feeling a little bit more comfortable with the idea of calculating these divergences and using the del operator. So let's use that knowledge to make calculations and see what does this lead to a simpler expression and something which we can make sense of? So we have del tau tau x I plus tau tau y j plus tau tau z k. That's del operator, which operates on the gradient of f. And the gradient of f is tau f tau x I plus tau f tau y j plus tau f tau z k. And all we need to do is calculate the dot product. Now, as we've emphasized in the previous videos, since I, j, and k are orthogonal directions, the only terms which remain when we take the dot product, the residual terms that remain are the ones that come from dotting I with I, j with j, and k with k. And all the other terms vanish because I dot j is equal to j dot k equals k dot I are all 0. So let's look at dotting this term with this term. And this gives us a new term, which is tau 2f tau x squared. It's just the second partial derivative of the function f with respect to x. So that's tau 2f tau x squared. Plus, we'll get one term from dotting tau y with tau f tau y. And this gives us the second term, tau 2f tau y squared. Plus, we dot these two terms and we obtain tau 2f tau z squared. Now, as you can see from this expression, it contains second order derivatives of the function f. In this case, it's partial derivatives of the function f with respect to x, y, z respectively. And that's why this is an example of a second order derivative. And this particular derivative has a special name. This is often abbreviated and written as del square f, where the del square comes from the notation that you're sort of dotting the del operator with itself to obtain del square. So you obtain del square f, which is the divergence of a vector is a scalar. So this is a scalar field. This is a scalar field. And this operator is called as a special name and is known as the Laplacian operator. This is called the Laplacian operator. And that's just the second order sort of del applied twice, del dot del applied on a scalar function. And in future sort of modules, we'll also cover partial differential equations, and you'll see that the Laplacian plays a very significant role in many of these sort of linear second order partial differential equations. So that's a new sort of second order derivative we've obtained. So far we've obtained two. One of them is the gradient of the divergence. The second one is obtained from the divergence of the gradient, and this leads to what is called the Laplacian. Now let's look at the third one. And now we have to calculate the curl of a gradient. So we need to calculate del cross del f. Now let's see what this gives us. So I'm going to use the determinant notation we worked out earlier. So we have I, j, k. The del operator is tau tau x, tau tau y, tau tau z. And we already know what the gradient is. That's tau f tau x, tau f tau y, tau f tau z. So when we expand this out, we obtain as the first term, I is the partial derivative of tau f tau z with respect to y. So we obtain the second order derivative, but this time this is a mixed second order derivative. It's composed of taking the derivative with respect to z first, and then the derivative of what we obtained, the tau f tau z with respect to y. And this is called a mixed second order derivative. So this term is a mixed second order derivative. Mixed, and it's called mixed because we have two different coordinates y and z mixed together in the denominator, as you see it. Mixed second order derivative. All right, so the first term we obtain is tau 2f tau y tau z minus we have tau 2f tau z tau y. So the only difference between this term and this term is that the order of operation, order of taking the derivative with respect to z and y have been interchanged. Now it turns out that for a lot of the functions which we encounter in physical applications, these two mixed derivatives, that is changing the order of the derivative with respect to y and z or z and y, and in the same way with respect to x and y, yx or xz and zx, the second order mixed derivatives turn out to be equal. That is to say that it doesn't matter in which order we differentiate a scalar function with respect to y and z, whether I calculate dou f, dou z first and then take its derivative with respect to y, or I calculate dou f, dou y first and then take its derivative with respect to z, it turns out that the result is the same. This may not be very obvious, and in fact, you can construct some functions for which this is not true. But just to sort of clarify, for most functions which we encounter, it turns out that these mixed derivatives are actually equal. What that gives us, so let me just work out this entire del cross del f, and let's see what all the remaining two terms are, and then we'll arrive at a conclusion. So the second term, which is the jth component of this derivative, will have minus j, and then you have dou 2f, dou x, dou z. That's coming from this, and this, minus dou 2f, dou z, dou x. And again, we see that these are mixed derivatives with x and z interchanged. And then the third component, the kth component, would be dou 2x, or rather dou 2f, dou x, dou y, minus dou 2f, dou y, dou x. So this term is also a mixed derivative with x and y interchanged. So if you trust the observation that for many classes of functions which we will come across with, we find that these mixed derivatives are actually equal. And actually, as a follow-up to this module, I'll put up a short quiz where you can just try out this equality of the mixed derivatives for yourself and convince yourself that this could indeed be the case. It turns out that each of these terms is just zero, which follows from what is called the equality of mixed derivatives. Quality of mixed derivative. And when this is true, that these terms, all of these terms are actually zero, it turns out that the curl of the gradient is zero, which is a very, very good result for us, which means that this particular combination will always evaluate to zero. All right. So of the 5 different second order derivatives, we have seen that one of them, number 1, exists. Number 2 gives us the Laplacian. The curl of a gradient is always zero for most classes of functions. And so this, I'll just write it in words. Curl of gradient, curl of grad, it's something called in shorthand notation, curl of grad is zero. So that brings us to the fourth kind of derivative, which is the divergence of the curl. So let's see what that gives us. So now we need to evaluate the divergence of a curl. So let's first evaluate what is the curl of a vector, and then we'll take the divergence. So let's evaluate what is del cross V. And I'll just write down again, I, j, k, dou x, dou y, dou z. And then let's say that the 3 components of V are Vx, Vy, Vz. You expand this determinant, and we'll find d dou Vz dou y minus dou Vy dou z. That's the first component, minus j. Then we have dou Vz dou x minus, so that's coming from this and this, minus dou Vx dou z plus k. And that's dou Vy dou x minus dou Vx dou y. So that gives us the curl of V. And now we need to take the divergence of this expression. So the divergence is the dot product with the del operator of this expression. So we'll have, so I'll just look at the I dot I, j dot j, and k dot k terms. And again, dou we know is dou xi plus dou y j plus dou zk. So which means that the first term we'll get is the xth partial derivative of this expression. So we'll have the first term as dou x of the first term here. So that's Vz. And then we end up obtaining a mixed derivative, right? So we have dou Vz dou y, and we take its partial derivative with respect to x, and that gives us dou Vz dou x dou y. Minus, we'll have the x partial derivative of this expression, which will give us dou 2 Vy dou x dou z. Now remember, this is the divergence of the curl, right? And this will give us, overall, when we work out all the expression, it'll give us a scalar, right? So we don't have any ijk's remaining after we've taken the dot product. So the first term is this. The second term we'll obtain from here. We'll take the yth partial derivative of both the terms appearing in this expression, and that gives us tau 2 vz tau y tau x minus tau 2 vx tau y tau z. And so this comes from here, this comes from here, and then we are just left with this term. So let's calculate. And what we need to do is we need to take the partial derivative with respect to z of both these terms. So this will give us tau 2 vy tau z tau x minus tau 2 vx tau z tau y. So let's look at all the terms that we have with us. We have tau 2 vx tau z tau y with a minus sign. But if I look at this term, that's also tau 2 vx tau y tau z. And if v is again a somewhat well-behaved function, the partial derivatives will turn out to be equal, which means that this term cancels this term. Similarly here, we have tau 2 vy tau z tau x with a plus sign, and we have tau 2 vy tau x tau z with a plus sign. Again, if the mixed partial derivatives are equal, these two terms cancel out. So that goes away. And then here we have tau 2 vz tau y tau x and tau 2 vz tau x tau y. Again, these are the same mixed derivatives. So if they are equal, these two terms also cancel out. So in the end, what we obtain is that the divergence of the curl is also 0. So if you go back to this expression, we found that this term is also 0. So of the 5 different second order derivatives, 2 of them are pretty much always 0 for most well-behaved physical functions. One of them is the Laplacian, and this one, it doesn't have a special name. It's just the divergence of the gradient. And so that leaves us with the fifth and final second order derivative. And I'll just write down what this is called. This is sometimes called the divergence div of curl is 0, right? So now we're left with the fifth and final expression, which is the curl of a curl. And I think I'm going to leave this as an interesting exercise for you to do. And maybe I'll put it up as part of the next quiz, which we have. So where you'll have to show a couple of things. One is the equality of the mixed partial derivatives for so maybe a couple of examples. And then maybe you need to work out, you can try working out what this will give us. It turns out that this particular expression will be a combination of terms which we have already seen, right? So it'll give us a combination of second order derivatives, which we have already seen. One of them will be a Laplacian. So it'll give you something like this. And the other one will be something you need to work out. So I leave it here, and hopefully you'll try out the next quiz. And again, as always, if you have any questions, if you feel that there's some steps you're getting stuck with, please reach out to me, and I'll be happy to schedule a one-to-one call with you and discuss and clarify and hopefully clarify your doubts. So hopefully, and in fact, this particular module exhausts all the possible second order derivatives that we can construct with the del operator. It turns out that higher order derivatives like third and fourth order we rarely come across them, and it's just a bit of algebra. Once you understand the properties of the del operator itself, you can construct any of these higher order derivatives if you feel the need to, if you encounter it anywhere. So hopefully this was of some use, and please do try the quiz and reach out to us for any questions, any clarification. Thanks for watching.